All right, guys, so I am on page 63, looking at the warm-up for lesson 5. So hopefully you already tried number 1 here like you were supposed to. So writing in standard and vertex form. So I like to always think about this as a graph. So if I think about kind of right in the middle here, we have the point 0, 1, and then it goes up on each side. We have the point 1, 2, negative 1, 2, and so on. So I can tell I'd have a parabola, right? And my vertex is right in the middle here at 0, 1. So if I know that's my vertex, in order to write this in vertex form, right, we would have that x, and then I look at the x coordinate, so we would think about it as being plus 0 squared plus the y coordinate of the vertex, which is 1. Well, x plus 0 is really the same thing as x, so we just call this x squared plus 1. All right, y equals I should have. Okay, and this is it. This is the vertex and the standard form. There's nothing I could multiply out because that x coordinate of the vertex is 0. So this one is very, very straightforward. Both the vertex and the standard form would be x squared plus 1. Okay, next up, we're going to look at something called the quadratic formula here. So we're doing this in the warm-up because this is something you guys should have done and learned in Algebra 1 that we are going to need for this lesson. Okay. So the quadratic formula is what we use to solve quadratics when it is not able to be factored. So some quadratics can be factored, some cannot. So let's look at how we use the quadratic formula. So the quadratic formula, I'm going to write the formula up here. X equals opposite of b plus or minus the square root of b squared minus 4ac. Big giant fraction, everything over 2a. So make sure you highlight that, circle it, star it, something we're going to be coming back to this one here. Okay, so we're going to see how that applies down here. So basically, a, b, and c are the coefficients, right? This is 1x squared plus 5x plus 6. So here a is 1, b is 5, 6 is c. And we're going to substitute 1, 5, and 6 into this formula here. So we have x equals, so opposite of b, right now b is 5. The opposite of 5 is negative 5, plus or minus the square root of b squared. So b is 5. 5 squared is 25, minus 4 times a, which is 1, times c, which is 6, all over 2 times a. Here a is just 1, so it's just over 2. Okay, so that's our setup. And from there, we just have to keep simplifying. Okay, so opposite of 5, negative 5 here, plus or minus. We're going to simplify under that square root first here. So I'm going to do 25 minus, and then I'm going to figure out what this piece is. So 4 times 1 is 4. 4 times 6 is 24. All over 2. So a lot of this is just going to come down each step as we simplify. So negative 5 plus or minus. Well, 25 minus 24 is 1, so we have the square root of 1 all over, 2. And now here's where it kind of branches off and may be different. So here we have a square root we know. We know the square root of 1 is just 1. Okay, so sometimes we may end up with numbers here where we cannot figure out the square root. We'll see one of those over in number 2. But if we can, we do. Okay, so this plus or minus business means I'm going to get 2 solutions, one from the positive version, one from the minus. So I'm going to set up 2 equations, one using the plus sign, so 5 plus 1 over 2, and the other using the minus sign, so 5 minus 1 over 2. So here we get on top, 5 plus 1 is 6 over 2 is 3. Okay, so I have a solution, an x-intercept, a root at 3. Over here, 5 minus 1 is 4 over 2. 4 divided by 2 is 2. So I have a solution, a root, an x-intercept at 2. These are my 2 solutions. Okay, let's try it with another one here. So here a is 2, b is 1, c is negative 7. So let's set this guy up here. So we have x equals opposite of b, so the opposite of 1 is negative 1, plus or minus the square root of b squared. 1 squared is just 1, minus 4 times a, which is 1, times c, which is -7, all over 2 times 2. All right, so let's keep going here. So we have -1 plus or minus. Let's simplify under that square root a bit. So we have 1, let's see here, -4 times 1 is -4, times -7 is, oops, I messed up, didn't I? Hopefully you guys were yelling at the screen. A is 2. There we go. So -4 times 2 is -8. -8 times -7 is a positive 56. All over 2 times 2 is 4. All right, keep going here then. -1 plus or minus under that square root. 1 plus 56 is 57 over 4. Okay, so at this point, I know 57 is not a perfect square. I would try and break down the square root of 57 if I could. So like what times what is 57? However, in this case, 57 is a prime number. The only thing that gives me 57 is 1 times 57. So in that case, actually, I had to pause for a second. I lied. 57 is not a prime number. 57 is equal to 3 times 19. 3 and 19 are both prime numbers. So if I did the square root of 3 times 19, there's nothing I can take out. There's no matching pairs. So the square root of 57, it's not prime, but it does not break down at all. So it's going to remain the square root of 57. So this, I can't go any further. This is how we would leave our answer. Okay, next page here. So getting into the meat of lesson 5. So we are going to be working a lot with the square root of -1 today. So let's jump to page 67 is what I want to look at. So where it says part 2, imaginary and complex numbers. So it says in the previous lesson, to be determined, you found that the quadratic formula gives the solutions to the equation. So they looked at this equation and we end up with these big ugly solutions, right? They were not beautiful numbers. They ended up with this after solving. Because the square root of a negative number has no defined value as either a rational or an irrational number, Euler, who was a famous mathematician, proposed that a new number, I equals the square root of -1, be included. This is going to be the most important thing for us here today. I equals the square root of -1. Okay, and we call that the complex number system. All right, so based on Euler's definition of I, meaning that I is equal to the square root of -1, we want to know what I squared would be. I squared is also going to be of importance to us. So if I think about squaring I, well, I is equal to the square root of -1, right? We see that up here. So when I square that, a square root and a squaring cancel each other out, and we are just left with -1. In other words, I squared is equal to -1. Okay, so let's see how we're going to use that down here. Okay, so with the introduction of the number I, the square root of any negative number can be represented. For example, if you're dealing with the square root of 2, right, the square root of 2 is the same as the square root of 2 times -1, which is the same thing as the square root of 2 times the square root of -1. Okay, so when I'm dealing with multiplying under a square root, I can break them into separate square roots. So the square root of 2 times I, which is sometimes written as I'd say more commonly written as I square root of 2. All right, it works when we have perfect squares as well. So -9, we see they split that up into the square root of 9 times the square root of -1. Well, the square root of 9 is just 3. The square root of -1 is I, so that becomes 3I. So what we're going to be interested in today is doing operations with this number I. So it says find the values of the following expressions. Okay, so these are all a little bit different. We just have to look at what we're given here. So first up, I have the square root of 2 times I squared. So I know that when I square something, it means I need to multiply it by itself. So the square root of 2I times, and they have a little multiplying in between it, doesn't really matter. The square root of 2I. Okay, this is all just one big giant multiplication problem. Notice there are no pluses or minuses anywhere in there. So this is the same thing as saying like the square root of 2 times the square root of 2 times I, right? I'm just rearranging the order of them writing that in. And this is helpful for us because the square root of 2 times the square root of 2 is the same as the square root of 4. I times I is I squared. I know the square root of 4 is 2. I know I squared from up here is equal to negative 1. So 2 times negative 1 is negative 2. So that all simplifies to negative 2. Let's look at another one. 3i times 3i. So a lot of times we like to multiply the numbers together and the i's together. So 3 times 3 is 9. I times I is I squared. So 9, we know that I squared is equal to negative 1. So 9 times negative 1 equals negative 9. So what you may be noticing is all I squared really does, because it's negative 1, is just changes something from a positive to a negative, or it'll also work the other way around. Okay, next page, please. Okay, so numbers like 3i and 2 square root I are called pure imaginary numbers. So they just have an imaginary part to it. Remember we talked about there are no pluses or minuses. Numbers like negative 2 minus I and negative 2 plus I that include a real term and imaginary term are called complex numbers. Complex numbers are not real numbers. They do not lie on the real number line. That includes all of the rational and irrational numbers. Also note that the real numbers are a subset of the complex numbers, since a real number results in an imaginary number, or an imaginary part of a plus bi is 0, that is a plus 0i. Okay, all that's saying is every single number is a complex number. A complex number includes a real part and an imaginary part. If your imaginary part is 0, then you just have a real number. Okay, operations with complex numbers work the same, follow the same properties. We really have to pay attention to the i's. So we're going to look at some examples here with like adding, subtracting, combining like terms, all that jazz. So they give us an example, 3 plus 4i. So this is one imaginary number. 5 minus 2i, this is a second imaginary number. When I'm adding these, all I'm really doing is combining like terms. So I'm adding the real parts. 3 plus 5 gives me 8. And I'm adding the imaginary parts. 4i plus negative 2i gives me 2i. Okay, so it works the same just as combining like terms with a polynomial. All right, subtracting, same idea. We're just going to have to distribute this negative here. So notice they did that here. They've got a negative in front of the 3. The 5i was negative and it became positive. Then they combine like terms. 7 and negative 3 is 4. 2i and 5i gives us 7i. Okay, so let's try a few here. These are very straightforward. So I have two imaginary or complex numbers I'm adding, so I'm going to add the real parts. 13 and negative 12 gives me 1. And then the imaginary parts. 2i and negative 5i gives me negative 3i. And that's it. Let's look at another one. So I'm adding. So when I add the real parts, negative 7 plus 3 is negative 4. And add the imaginary parts. 12i and negative 6i gives me a positive 6i. Okay, subtracting the same idea. You just want to distribute first here. Okay, so this is really 8 minus I minus 7 plus 3i. The signs of the second one just change. So 8 and negative 7 gives me 1. I and 3i gives me 2i. All right, last one here for this type. So negative 9 plus 4i, and I'm going to distribute that negative, which just changes the sign. So we get negative 9 plus 4i. So when we combine the like terms, we get negative 9 and negative 9 makes negative 18. 4i plus 4i gives us 8i. All right, so that's adding and subtracting. Let's look at multiplying here. So multiplying is really just a lot of distributing. So some of you may choose to use the box. Some of you may just distribute. It's up to you. So let's jump right into an example here. So with number 9, so I've got 3 plus 2i times 5 plus 7i. So I like to distribute here. So I'm going to do 3 times 5 first to give me 15. Plus 3 times 7i. So 3 times 7 is 21. So this would be 21i. Right, and then I do it with the 2i. So 2i times 5 is 10i. And 2i times 7. So this one's a little bit different because there are two i's. So first I'm going to do 2 times 7 is 14. And then I times I is just I squared. Okay, so we've got a little bit of work to do here. So I'm going to bring the 15 down. I also have some like terms. 21i plus 10i is 31i. Plus 14. Now we have to remember I squared is equal to -1. So really, this is 15 plus 31i minus 14. And then you notice we have some like terms to combine. 15 and -14 is just 1. So this is 1 plus 31i. Whoops. There we go, 31i. Okay, so when you're multiplying and adding and subtracting, you should never, ever, ever have an I squared in the end. Okay, you should always have your real part, which is just a number, and your imaginary part. There would never be anything with an I squared. All right, let us try another one here. So, distributing. 10 times 4 is 40. 10 times -6i is -60i. -3i times 4 is -12i. And -3i times -6i. So -3 times -6 is a positive 18. I times I is I squared. All right, so combining like terms, -60i and -12i gives us -72i. And plus 18, I squared is equal to -1. All right, in other words, right, we've got 40 minus 72i. I feel like my eyes get worse every time I write them. Minus 18. So I can combine the 40 and the -18 to give me 22. And then I still have the minus 72i. Whoa. Okay, so in a nutshell, that is multiplying. So there is kind of a unique case that comes up sometimes. So it says these two complex numbers are called conjugates because they are the same except the opposite sign on the second term. So see how I have 4 plus 2i, 4 minus 2i? These are conjugates. They're the same thing except the signs in the middle are opposite. So let's see what happens when we multiply these. All right, so we have 4 times 4 is 16. 4 times -2i is -8i. 2i times 4 is positive 8i. And then 2i times -2i is -4i squared. Okay, so what you'll notice is -8i and positive 8i cancel each other out. So I'm left with 16 minus 4, and I'm going to replace I squared with -1. Which really means I have 16. -4 times -1 is positive 4, which is just 20. Okay, so what happens is that imaginary part is gone. And I just have a real number. Okay, next page, page 70. We have it's just continued here, so another example. So let's go ahead and go ahead and multiply. So 3 times 3 gives us 9. 3 times -5i is -15i. 5i times 3 is 15i. 5i times -5i is -25i squared. So again, those I pieces cancel out. So we have 9 minus 25, and I'm going to replace I squared with -1. So it's really 9 plus 25, which is 34. So C asks, what do you notice about the answers? So what you should be noticing is that the imaginary part is gone, right? There's no imaginary parts left. In other words, the imaginary part cancels out. Okay, so we're going to tie this all into that quadratic formula that we were talking about earlier. So it says, given the function, so here's our function, find x such that f of x equals 0. In other words, what value can I plug in for x that it would give me a 0? So what you'll notice here is I just graphed that in decimals, x squared plus 4x plus 5. And notice it never ever touches the x-axis. So this is a clue for us that there are not going to be any real solutions. It's not going to be factorable. Our solutions are going to be imaginary, which is where that I is going to come in. So let's go ahead and look at it. We're going to do the quadratic formula. Okay, so A is 1, B is 4, C is 5. And feel free to look back at that formula if you need it. Okay, so x equals the opposite of b plus or minus the square root of b squared. So if b squared is 16 minus 4 times a, which is 1, times c, which is 5, all over 2 times a, which is just 2. All right, then we'll keep going here. So negative 4 plus or minus the square root of, we've got 16. So let's go ahead and do that multiplying. So negative 4 times 1 times 5 is going to be a negative 20 over 2. Okay, next up we do the subtracting under the square root. So 16 minus 20 gives us a negative 4. So we can see where this is imaginary, right? I have a negative under the square root. Remember, I is equal to the square root, the square root of negative 1. Okay, so what I want to think about here, the square root of negative 4. Well, the square root of 4 is 2. The square root of negative is I. So this is really negative 4 plus or minus 2I over 2. So again, that comes from the square root of 4 is 2. A negative under the square root gives me I. Okay, so we're almost done here. Let's come this way. So this one happens to simplify a little more. So sometimes we're stuck with this just like it is. But this one, it would be simpler if I broke this into two fractions because both of my parts on top are divisible by 2, which is what I have at bottom. So I'm going to break this into two separate fractions. And I would have that big plus or minus sign in between them. Okay, so we end up with negative 4 divided by 2 is negative 2. Plus or minus 2I over 2. The 2's cancel, and I'm just left with I. So my solutions are negative 2 plus I and negative 2 minus I. Okay. So we are going to skip over 12 and 13. And next up here, for number 14, I want you to pause the video. So sub, please pause the video, and I want you guys to try number 14. Maybe give it about 5 minutes or so, and then play the video to see how you did. All right, so here's what I came up with. I plugged in A as 1, B as negative 3, C as 4. And I ended up with 3 plus or minus I square root of 7 over 2. So notice this one was not as beautiful. Under the square root, we got a negative 7. I can't break down 7 at all. It's prime, so it's just going to stay square root of 7. But that negative always comes out as an I. Here, some of you may have broken this into two fractions and written 3 over 2 plus or minus I square root of 7 over 2. And that's okay. In this case, we can't simplify anything at all, right, because 3 isn't divisible by 2, but it is okay to still go ahead and write it that way to always check. So if you left it like this or broke it into two fractions, I am okay with either way. All right, so the last thing we're going to look at then is going to be on the next page, so page 72. So we're going to look at the takeaways here to kind of look at some of our vocab for this lesson. So first up, x-intercepts. So x-intercepts are points where the graph crosses the x-axis. So if you want to draw yourself a little picture, it would be something like these points here. Let me put them in another color. So this point here where my parabola touches the x-axis. Okay. Roots then are x values that make the function equal to 0. Okay, so something important to note here, Every x-intercept when you plug it in the function would make it 0, but we also sometimes have imaginary solutions that make our function 0. Next up, if the graph of a quadratic function intersects the x-axis, so goes through the x-axis, we say the function has real roots and x-intercepts. The function has real roots and x-intercepts. All right, meaning it actually touches. All right. If the function does not intersect the x-axis, so that would be like one of our parabolas that maybe say opened like this and never ever touches the x-axis. Okay. If that's the case, we say the function has imaginary roots and no x-intercepts. Okay, so in other words, the function always has roots, whether or not it touches the x-axis. Sometimes it has x-intercepts, and those are also your roots. Sometimes it does not have x-intercepts, but it still has numbers, imaginary numbers, that you can plug in. That will make the function 0. All right, very last thing here to talk about is just a breakdown of the number system. So we talked earlier that every single number is a complex number, right? So we put that out in the big square here. And complex numbers are made up of imaginary parts and real parts. So imaginary parts would be anything that includes an I. All right, the real parts are the numbers you are used to seeing, and the real numbers, excuse me, break down even further. So real numbers break down into rational and irrational. Okay, irrational numbers would be things like the square root of 10 or pi, right? Cannot be written as a fraction. Rational numbers break down even further. They break down into integers, and whole numbers, and natural numbers. So natural numbers would be 0, or excuse me, not 0, 1, 2, 3, and so on. Whole numbers are natural numbers, just including 0, so 0, 1, 2, and so on. Integers includes the negatives. I'm going to say and so on. And rational would just include anything that can also be written as a fraction. So negative 1/2, or positive 1/2, negative 0.3, things along those lines. Okay, so at this point, you guys, if you have some time, can go ahead and start looking at the set that's on the next page. So it's a lot of operation type things. Okay, so if there are some that you look at and you're like, oh, I don't know how to do that, go ahead and save that one for Monday. I will be back Monday to help you with any of those. But some of these, like where you're just combining like terms, you guys should be able to go ahead and do. So with any time you have remaining in class, go ahead and look at pages 73 and 74 and do any of them that you feel like you know how to do.